Welcome to the video on the location of phase boundaries. So recall that the chemical potentials for two phases in equilibrium have to be equal to each other. Thus, if we have two phases, alpha and beta, in equilibrium, then the chemical potential of alpha at some pressure and temperature has to be equal to the chemical potential of beta at some pressure and temperature, where the pressure and temperature are the same for the two if they're in equilibrium. And so if we solve this equation for the pressure in terms of temperature, then we can get an equation for the phase boundary between phase A and phase B, alpha and beta, rather. So let's examine the phase boundaries in terms of their slopes, change in pressure per change in temperature. And we'll allow pressure and temperature to change infinitesimally, but in such a way as to keep the two phases, alpha and beta, in equilibrium. So we have a reversible change. These are small changes. So at all points along the phase boundary, then the chemical potentials have to be equal. So the change in chemical potential of phase alpha has to be equal to the change in chemical potential of phase beta. And also recall that the change in Gibbs energy is equal to VdP minus SdT. And thus the change in chemical potential has to be equal to the molar volume times the change in pressure minus the molar entropy times the change in temperature. Remember that we're adding these molar quantities because mu, the chemical potential, is the molar Gibbs energy. And so now by saying d mu, we're fixing that we have the molar Gibbs energy, a change in molar Gibbs energy, so we have to have molar volume and molar entropy here. And thus, then we can say that the molar volume of phase A times the change in pressure minus the molar entropy of phase A times the change in temperature has to be equal to the molar volume of phase B times the change in pressure minus the molar entropy of phase beta times the change in temperature. And so that's what we have up here again. And now we can rearrange this equation to get the molar volumes on one side and the molar entropys on the other. And so now we have the molar volume of phase beta minus the molar volume of phase alpha times the change in pressure is equal to the molar entropy of phase beta minus the molar entropy of phase alpha times the change in temperature. And so now we can relate the change in molar entropy and a change in molar volume to the change in pressure with respect to temperature. So now we have for macroscopic change, for macroscopic phase transition from alpha to beta, we have the change in entropy is equal to the molar entropy of beta minus the molar entropy of phase alpha. And then the change in volume for that phase transition is equal to the molar volume for beta minus the molar volume for alpha. And so now the change in pressure with respect to temperature is equal to the change in entropy for that transition divided by the change in volume for that transition. And so this equation is called the Clapeyron equation. And so the Clapeyron equation applies to any phase equilibrium of any pure substance, and this is exact, it's not an approximation. So let's look at the solid-liquid phase boundary. So melting or fusion is accompanied by a molar enthalpy change, delta H of fusion, and it occurs at some temperature T. Now the molar entropy of melting at this temperature T is thus given by this. So we have the molar entropy of fusion. So that's the change in entropy for the molar change in entropy for the melting process is equal to the enthalpy of fusion divided by temperature. And then we can change our Clapeyron equation from this to, we can substitute in for our our change in entropy. We substitute in the change in enthalpy divided by temperature to get this quantity. So now, as the enthalpy of fusion is positive, so this value has to be positive, except for helium-3 under some conditions. And the volume change is usually positive for melting, not always, but usually. And the volume change for the melting process is always small. It's not like the volume change for the vaporization process, which is large and positive. This means that the slope is steep, and it's usually going to be positive. So this is why on the phase diagram we have for the melting curve, it's always a very steep slope. It's usually positive slope. Sometimes, like for water, it's a negative slope, because for water this value, the change in volume is negative for the melting process because the density of water, liquid water, is slightly higher than the density of ice, solid water. So now we can obtain the formula for the phase boundary by integrating dp dt, and we can assume, or we will assume, that the enthalpy change and volume change don't change significantly with temperature and pressure. So we're assuming that they're constant, which means we can pull them out of the integral. So if the melting temperature is T star, when the pressure is P star, and if the melting temperature is T, when the pressure is P, then we get this integral. So note that we've pulled out the enthalpy of fusion and the volume change for our transition. There should be fusion there too. We've pulled those out of the integral because we're assuming that they don't change with temperature. So the approximate equation for the solid liquid phase boundary is this. Note that this is approximate because now we've pulled this quantity out of that integral. So this is just an approximation now. So now we have pressure is equal to the initial pressure P star plus the enthalpy of fusion divided by the change in volume for the melting process times the natural log of the temperature divided by temperature star. So if the temperature is close to T star, then we get this approximation. We make this approximation, and so now our natural log is approximately equal to this value, T minus T star over T star. And therefore we can change our equation to be like this. So this equation is a steep straight line on a plot of pressure versus temperature, and so that's why the solid liquid curve looks like this. All right, so now let's look at the liquid vapor boundary, vapor phase boundary. So remember that the molar entropy change for vaporization is equal to the enthalpy of vaporization divided by temperature. And then the Clapeyron equation, which was this, we can then substitute in for our change in entropy, our molar change in entropy for vaporization to get this. And now the enthalpy of vaporization is positive, and the change in volume is large and positive. So remember, for the vaporization process, the change in volume is always going to be positive because the liquids always take up significantly less volume, less space than the gas phase does. And so now the slope of our liquid vapor phase boundary is going to be positive, but it's going to be significantly smaller than for the solid liquid phase boundary because that change in volume is much larger, and so our denominator here is going to be much larger. So it follows that dt dp is large, and thus the boiling temperature is more responsive to pressure than the freezing temperature is. So as we change the pressure, the boiling temperature is going to be affected much more dramatically than the freezing temperature will. So, because the molar volume of a gas is so much greater than the molar volume of a liquid, we can approximate the change in molar volume as just the molar volume of the gas. So we're ignoring the molar volume of the liquid here, because the molar volume of the liquid is going to be so much less than the molar volume of the gas, we can ignore it. So if the gas is an ideal gas, then we get the molar volume of the gas is equal to RT divided by P. So using these two approximations, then the Clapeyron equation becomes this equation. So dP dt is equal to the enthalpy of vaporization divided by the temperature times the quantity RT over P. So R the gas constant, T the temperature, and P the pressure, which rearranges into what we call the Clausius-Clapeyron equation for the variation of the vapor pressure with temperature. So now we get the Clausius-Clapeyron equation. So the change in the natural log of pressure with respect to temperature is equal to the enthalpy of vaporization divided by R times the temperature squared. So note that in going from here to there, we've used this relationship. So the Clausius-Clapeyron equation is just an approximation, unlike the Clapeyron equation, which was exact. But the Clausius-Clapeyron equation is nonetheless important for understanding the shape of phase diagrams. We note that the shape of that liquid-vapor phase boundary is curved, something like this, and it has a much lower slope than the liquid-solid phase boundary. So the Clausius-Clapeyron equation also allows us to predict how the vapor pressure varies with temperature and how the boiling temperature will then vary with pressure. So if we assume that the enthalpy of vaporization is independent of the temperature, then we can integrate the Clausius-Clapeyron equation, and we can pull our enthalpy of vaporization out of, and R out of the integral, because those are then constants. And then we get this value. So then, because the integral on the left, so that's this integral, evaluates to the natural log of pressure divided by pressure star, P star. Then we get this. And so now we get P equals P star times E to the minus chi, where chi is the enthalpy of vaporization over R times the quantity 1 over temperature minus 1 over temperature star. So for some generic liquid vapor phase boundary, we've plotted that over here. So again, we get this upward curve to it, and note that the slope at all points is significantly less than the slope for the solid liquid curve, whether it have a positive slope or a negative slope. All right, so now let's look at the solid vapor boundary. So this is the sublimation curve. So the only difference between this case for the solid vapor and the liquid vapor phase boundary is that the enthalpy of vaporization needs to be replaced by the enthalpy of sublimation. And so now remember that the enthalpy of sublimation is equal to the enthalpy of fusion plus the enthalpy of vaporization. So the amount of energy it takes to go from the solid to the gas. Remember, in going from solid to gas, we're breaking all of the intermolecular bonds. In going from the solid to the liquid, as in fusion, we're breaking just a few of the intermolecular bonds, those intermolecular forces. And then as we vaporize from the liquid to the gas, we're breaking all of the rest. So breaking all of the bonds takes exactly as much energy as it does to break some of them and then to break the rest of them. So the slope of the sublimation curve has to be larger than the slope of the vaporization curve for similar temperatures because it takes more energy because that enthalpy of vaporization is larger. So a generic phase diagram is plotted over here. So now we have our very steep solid liquid phase boundary. We have our much shallower liquid vapor phase boundary, and then we have our solid vapor phase boundary. Where note that near the triple point, then the slope of our vaporization, of our sublimation curve is higher than the slope of our vaporization curve is. And that's the location of phase boundaries.